All right, so there's a unit tangent vector. And principal unit normal. Let's talk about the unit tangent vector. So if you have a vector valued function r of t, then we learned so far that differentiating it gives you the velocity vector, which is tangential to the trajectory of the r. Right? Now, in some cases, you want to have a standard size tangent vector, and that one is called the unit tangent vector. The unit tangent vector, this unit means what? What does unit vector mean? Length 1. Okay, so that's all it means. So you have this t hat, and this hat is the symbol that it's a unit vector, okay? Which is taking the v, and what should I do? Divide it by its size. So that's a simple thing. Okay. Now, short quiz. What's this equal to? One. That's a simple question, right? We've been talking about this all along. Unit, right? Unit means length is 1. Yeah. So it's just circular reasoning here. But there is something I wanted to show. First is that if you have this, you can say that t squared is 1 squared, which is just 1. And then you also know that v dot v, any vector dotted with itself is its norm squared. That's because any vector dotted with itself is norm of each times cosine of the angle between, but what should I go in here? What should I put here? 0, because it's the same vector, right? And cosine 0 is 1. So any vector dotted with itself is same as its norm squared. And sometimes you want to do the opposite. You want to rewrite norm squared as the vector dotted with itself. So let me rewrite this as t dotted with itself is equal to 1. And then I also have to use something called the product rule for dot products. And that's another thing that I didn't mention until now. If you have two vectors u and v, and let's say they're both vector value functions really, for different values of t, you have vectors u and v. Okay? So these are both like RT that we've been playing with. If you had to differentiate two vector valued functions which have the dot product, then it's same as taking dot of the derivative of the first dotted with the second vector plus ut dotted with the derivative of the second. What's more surprising is that you can replace dot with the cross product and it's still true. And the reason is, if you look at the proof of the product rule in Calculus 1, the only algebraic property that it makes use of is really the distributive property. So any kind of operation that satisfies the distributive property should have this product rule being satisfied. So another example, matrix multiplication. It has distributive property, and you can come up with a similar thing. Okay. All right. So we have that, and then if I apply it to here, what would that mean? That means t prime dot with t plus t times t prime equals to 0. And thankfully, dot product is commutative, whereas cross product is not. I can commute these two and end up with twice of this equal to 0, so that means t, the derivative of the unit vector dotted with the unit vector is 0. All right, what does that mean? If you have two vectors whose dot product is 0, what does that mean? They're perpendicular. So you have a perpendicular thing, and that's where this normal comes from. What does normal mean again? Perpendicular. Right? So if you have some three-dimensional curve, here's the picture. If you have the velocity and divided by its size, you have the unit tangent vector, whose length is 1. Right? And if you take the derivative of this unit tangent vector, because after all, it still is a function of t, right? Even if I did this, the top is a function of t, the bottom is a function of t. So in its entirety, it's a function of t. You can still differentiate this. If you differentiate it, you get another vector which is perpendicular to the original one.
Wait, how do you know if it's not going up?
Actually, so first of all, knowing perpendicular is not enough, because if you have a single vector, there are many different vectors that's perpendicular, right? Yeah. So it could be not only going up, but it could be here or there. Okay. And that's why for normal vectors there is this this adjective here. It says principal unit normal vector. So of all the kinds of normal vector that you can think of, normal to the t, there's a vector which is principal because it keeps track of which direction this curve is bending. So that's where this principle comes from. So let's see, if t is going this way, it's bending that way, then what's happening to the unit normal vector is it's moving, it's bending in one direction, right? And the derivative keeps track of which way it's changing. So this is perpendicular like that, and the principal unit normal vector is defined as taking this derivative and dividing it by its size. See, the really annoying thing is, even if you know that it's perpendicular, you don't know that it's a unit vector. So you still need to divide it by its size so that it is a unit vector. Okay. So after dividing it by its size, you can come to this thing called the principal unit normal vector. Okay. Next time we'll talk about some examples of